Welcome everyone to this turned out to be our first seminar of the winter semester, and still virtual. And just an announcement from me for MICDE. If you're an MICDE student in the CDE program, in the certificate in CDE program, or a fellow, we will put a link because we have a new form to signing just to record that you attended the seminar. So please fill it out, and we will post it a couple of times through the seminar just so everybody gets a chance to sign in. And thank you. And then I'm gonna let Professor Esedoglu introduce our speaker.
Okay, welcome everybody to this semester's joint AIM and MICDE seminar. We are delighted to have Professor Blaise Bourdin today, who has recently become our neighbor to the northeast, close to Toronto. After a number of years at LSU, he's now at the Math Department of McMaster University. And he's going to talk to us today about phase field methods for fracture.
Well, thank you, Selim, for the introduction, and thank you for the invitation. And again, I want to apologize for not being able to visit in person. I was actually really looking forward to be able to finally interact directly with people. The second part is, now that I have the title of my slides in front of me, I realized that maybe I should let others be the judge of whether there were successes in the past or not. But it is what it is. That's whatever. Okay, so what I want to do is to talk about the phase field models of fracture, something that I and others have developed over the last now almost 30 years. And I'm assuming that many in the audience are not familiar with fracture mechanics or phase field. So I will start by giving a quick construction or overview of how we came up with this type of approach. I'll do my best to show you that that actually works in many situations. That's the past successes. But I would also want to insist on the fact that there's still lots of work to be done in the field, and that's the current and future issues. Okay, and also want to iterate that you are absolutely welcome to interrupt if you have any question. Don't feel like you need to wait until the end of the presentation. Okay, all right, so first want to talk about fracture, what it is, why we want to study it, and then why we want to predict it. And so traditionally, when you think of fracture mechanics in engineering, what comes to mind, and if you look at the cover page of most fracture mechanics books, you'll see something similar to the top left corner of my first slide. So this one is the collapse of the overpass, the pedestrian overpass at the Florida International University in 2018. The sad part is that I keep on redoing this slide and adding a new man-made disaster instead of this one. And for the longest time, and still at large, the goal of the understanding of fracture in the computational engineering community is really preventing fracture. I mean, obviously, this is not something you want to see. And to a large extent, since the 1920s, 30s, 40s, most of the focus of the computational mechanics and mechanics and mathematics community has been to try to understand fracture from the optics that this is something that really should be avoided, and therefore it's not really important to understand the nitty-gritty detail of cryopropagation propagation. Cryopropagation propagation is bad. That's what many have been trained with and should be avoided. But the picture is really more complicated because fracture is something that happens absolutely everywhere. So the top right corner, so this is the schematic of a mining technique that is really used mostly in South America, I believe. It's called block caving. And the idea is to hollow out a mountain from the inside out by creating fractures so that boulders collapse. And then so that would be the core where the whatever you want to extract. You generate these cracks fall into this phenol and go all the way to the bottom when they're extracted. So here, fracture is the ultimate goal. You want to create cracks in some formation so that you can extract mineral resources. Having moved recently to colder climates, I discover or rediscover this thing called snow and ice. So the bottom left picture is an evolution of the ice cap over the Beaufort Sea. So Alaska would be somewhere around here, and that is the Northwest Territory. And again, so in this case, fracture is neither good or bad. It just happens. The ice caps are going to break, and with changes in climate, the fracture patterns of the ice shelf may change. And it's really important to understand or be able to predict, even if it's simply qualitative properties of the fracture of the ice cap. And the obvious would be, will there be a channel so that this route is navigable or not? But also, are there going to be small icebergs or big iceberg and so on? Bottom right is an oil painting. So it's an infrared picture of a detail of an oil painting. And so you see this wide gray lines. So these are the artist sketch. That's not what I'm interested in. But you see these thin black lines, and these black lines are these craquelure patterns. So there's this fracture of the paint itself, and they're caused by the fact that the substrate, the canvas, stretches at a different rate as the painting itself. And unfortunately, most of the artwork that we have has suffered some changes of an environmental condition at some point or another, so already has a fracture pattern. There's a huge community in the art preservation field that really wants to understand what is the impact of environmental condition on the aging of cracks, on the aging of fracture. And they want to answer a question as simple as, what temperature and what rate of humidity shall I store a painting so that they will survive, and so we can pass them to the next generation? So you see, in all these examples, it's not sufficient to say that fracture is something terrible we want to avoid. This fracture is really something we want to understand. And to me, understand means being able to predict. Okay. So with that, we'll start to build a theory to do that. And so the theory that I'm going to build is based on the idea of Griffith. So that's a theory that started in the 1920s. And I'm going to read some kind of, to give some kind of rewritten version of history, mostly because I want to use modern mathematics to describe all papers. But a current formulation of the problem would be the following. So you have a linear, brittle, elastic material. So linear means small deformation, that the stress and the strain are proportional to each other. Brittle elastic means that this material can behave in two different ways. It can stretch in a perfectly reversible way, or it can break sharply. And one way to think of a brittle material, if you can break something and glue it back in place, it's brittle. So ceramic is brittle, but an alloy at high temperature, which is going to have some plasticity, permanent deformation, and so on, is not a brittle material. I'm going to assume that everything happens slowly, so that's a rate-independent hypothesis, because everything happens slowly. Speeds are not really involved, but it's convenient to keep track of something that I will call time. Think of time as simply a quantity that flows only one way, and it describes that the fracture phenomena that I'm trying to describe don't depend on any velocity. But if you play a movie backward, you definitely see if something is, you don't want to see pieces of the material going back to their initial configuration. Okay, my material is going to submit to some boundary displacement on some part of the boundary. And I'm going to start assuming that I have a single crack that propagates along a given path. So I'm going to go gamma tilde, the known path of the crack. Going to assume that my crack only has one free end that moves along gamma tilde. So identifying the crack gamma of L would be equivalent to finding the curvilinear coordinate of its tip or the crack length. So my ultimate goal at this point is for any pseudo time t, finding the crack length L and the equilibrium displacement U. So we're going to do that step by step. The first step is going to not worry about the crack, but just look at the equilibrium displacement. So what we're going to do is we're going to fix the displacement. We're going to do the prescribed displacement. We're going to fix the crack length L. And okay, classical theory of continuum mechanics tells you that given T, so the loading, and L, the crack length, and if you know L, again, you know gamma of L in this at this stage, the equilibrium displacement minimizes the mechanical energy. So that's the 1/2 of A E of V E of V is called a strain energy density associated to a displacement V. The E is the symmetrized gradient, that's also called a linearized strain. And so assuming, so again, knowing the boundary displacement and the crack length, if you minimize this, we'll call U, where is it written? U of T and L, the minimizer of this energy. And the value of the energy, so F of U of T and L, is the potential energy, that is the mechanical energy associated with the equilibrium displacement. Okay, so this is just elastostatic. And if you're not really familiar and you're a bit intimidated with the A and the E, just think 1/2 of gradient V squared, where V is scale. That's what's fine. Okay. So Griffith's argument in the paper from the 1920s is based on introducing two quantities. So the first is the elastic energy release rate. That is the partial derivative of the potential energy with respect to the crack length. So if you think a little bit, if you increase your crack length, then well, along the crack, displacement don't have to be continuous anymore. So the space of admissible displacement becomes larger. So the value of at the minimizer becomes smaller. So P of L, you expect that it's at given T, sorry, P of T and L should be a decreasing function of L. And so we're going to use its opposite. So G is negative dPdL. Again, the right way to think of that is you fix the load, you do a small crack increment, and you measure the reduction in potential energy. So it's the released energy, elastic energy, that is released by a crack increment. The second argument is to say that in order to grow a crack, well, you need to do something. So the most basic version would be to say, well, I need to cut some atomic bonds between molecules. That's what forms a crack. And the cost of doing that in 1D is going to be in 2D, so it's going to be proportional to the length of the crack. A more modern view would be what happens near a crack is terribly complicated. You have process zone, you have lots of tiny crack. You may have some change in the crystalline structure if you're looking at the metal or whatever. But we're going to linearize all of that and postulate that there's an ad hoc quantity called the GC, that is such the energy dissipated for growing a crack by an increment of length delta L is GC times delta L. Okay, so these are our modeling choices. And the last part is simply a stability principle. And I'm really just reformulating Griffith's 1920s paper. And the argument is first, well, in the class of material that we're interested, cracks only grow. So if Li is the L at time Ti and the Ti are a set of discrete snapshot, Li plus 1 should be greater than Li. And the second argument, we're going to test potential, we're going to test any potential crack length Li plus 1 for stability. And the way we do that is we assume that we know Li and Ti. We increment the loading. So we now go to the time Ti plus 1. And we say if Li plus 1 is the crack length at this time, we can get a small crack increment, delta L. And we can compare the energy of a configuration consisting of a crack of length Li plus 1 plus delta L. So what is it? Well, it's going to be P at the new time step and for the crack length Li plus 1 plus the increment. But in order to achieve that, you also need to spend some energy, Gc times delta L. So the energy after the increment should be this term. And the natural argument is that Li plus 1 is a stable crack length at time Ti plus 1 only if the potential energy of Ti plus 1, Li plus 1 is less or equal than this quantity. That's a standard stability argument. It looks like Euler, the way you construct Euler-Lagrange equations. Okay, if you move everything to the right-hand side, divide by delta L, send delta L to 0, this formally, what you get is minus dp dl at Ti plus 1, Li plus 1, minus Gc must be negative, or G minus Gc must be negative. Now, if you wanted to take a negative crack increment, well, you have to be really careful because you cannot necessarily, in particular, if your crack was stalling, the idea of taking a negative crack increment would be a contradiction with the crack growth hypothesis. So what we're going to do is we're going to assume that the crack grows and say, if Li plus 1 is greater than Li, then I can take an admissible test crack length, which is Li plus 1 plus delta L, but where delta L is small enough and negative. Do the same argument. So if your stability mandate that P of Ti plus 1, Li plus 1 is less than the energy of the modified configuration, move everything to the right-hand side, divide by delta L. Remember that delta L is now negative, and you get the opposite inequality from before. Okay, so if I put everything together, we get what I call the Griffith system, even though Griffith himself never wrote that, but you could describe the evolution of, or the discrete in time evolution of a crack obeying Griffith's idea of stability as a system of three equations. First, that the crack must grow, G must be always less than Gc, and if Li plus 1 if Li plus 1 minus Li is non-zero, then G must be equal to Gc, and you can combine this in this form. Okay, so of course, if you read this in 2022 or 100 years after Griffiths, with any mathematical training, you probably recognize that this looks like KKT condition for a minimality problem. But now you have to keep in mind that KKT is about 1956, if I remember correctly. Here we're talking about something that dates from the 1920s. So the connection between this system of equation and the minimization problem, that is the minimization of an energy that is the potential energy plus Gc times L, could not be done at the time where this principle was established. Okay. So again, now looking at this, instantly we should think that this looks like the optimality condition for the minimization of the potential energy associated with a displacement field V and a crack length L, and that is so potential energy here plus Gc times L under a growth constraint. Instead, for almost 70 years, what was done is what is often called the linear elastic fracture mechanics, which is, in my opinion, a poor name because it's not a linear theory. But the way fracture mechanics has been done for many, many years is to postulate the crack path. Remember, in all of that, I assume that gamma of L was given. And to simply postulate a simple criticality condition, a crack grows if G is equal to GC. And then the game between how do I compute G and how do I compare it to GC? Well, the way to compute G, it typically has been to link the elastic energy release rate with the singularity of the elastic displacement of the crack tip. That's the stress intensity factor. And that was done by, among other, Irwin, that links these two. Then find a way to compute this stress intensity factor. This is usually done through something called a J integral by Jim Rice and so on. This is a great theory in the sense that it really led to major accomplishment, but it still have many limitations, especially in light of what I was discussing earlier, what we would like to do, particularly the fact that you need to assume a crack path, which is completely unreasonable. Think of the block caving mining. We don't know where the cracks are going to go, and that's what we would want. Or the fracture of the ice shelf. We want to know where the cracks are going to go. And for some reason that I won't really describe it, it's also very, so this type of theory behaves very poorly if you want to study really complicated problem when you have change in fracture topology. So a kinking, a branching, or merging of cracks, or crack that may not be very regular in space or in time, and so on. So what can we do instead? Well, in the mid-90s, the math community became really enamored with so-called free discontinuity problems, and many of them came from the image processing community. But the idea was to apply this theory to Griffith's fracture, and in particular, Foinfort and Marigot in '98 in France really proposed to do the following. Instead of postulating the crack path and minimizing the so-called Griffith energy, why don't we take the energy for what it is, the sum of the mechanical energy plus GC times the crack of times the length of the crack, and minimize it with respect to what? With respect to any admissible displacement and any crack set. So essentially, this is just being even more Griffith than Griffith, is to keep the essence, all the essence of Griffith, but postulate that the crack geometry itself should follow all the same criticality argument. There is over 25 years of the analysis of that, going from deriving free, weak form of the energy to get existence of solution, going from discrete in time to continuous in time, and so on. I'm not going to go through that, but just want to make clear that this is a problem that has been studied really, really carefully, and that for which there's lots of analysis that has been done. And so we know that this problem admits solution, and so on and so forth. That said, that doesn't tell us how to solve the problem. And that's finally where the phase field comes into the picture. So again, I recall the form of the energy. And remember that what we want to do is to minimize this energy E with respect to not only any displacement field, but only all crack geometries. So this is a difficult problem. So there are lots of ways to deal with displacement field that are not continuous across a given surface. But if the surface of discontinuity, the crack, is itself not known, then the choice of method is much more limited. And issues such as the ability to not only reproduce the position of a crack, but also its length, as silly as it looks, are actually something that are very complicated. But something that the image processing community had been thinking a lot at this point. And so what we did in the mid-90s at this point was to borrow this idea coming from the image processing community, and to build a phase field approximation of the Foinfort and Marigot's energy. That is to introduce an order parameter alpha that is a smooth function taking value between 0 and 1, a regularization parameter, two interpolation functions, so a function A that is monotonally decreasing from 1 to 0, W that is monotonally increasing from 0 to 1, both of them smooth, and postulating or constructing this energy. So here you see that U is now a smooth function. There's no jump of U, so the integrals are in omega, not in omega gamma. But U is a function in H1. Alpha is a function in H1. But what you can show is that this EL converges to the Freund-4 and Marigot energy in the sense of gamma convergence. And that implies that the minimizer of this converges to the minimizer of Freund-4 and Marigot. So this free discontinuity problem, which is a tricky problem involving minimizing with respect to a function and an unknown curve, is simply replaced by a standard problem of minimizing a function that depends on two, minimizing a functional that depends on two smooth functions. There are tons of variants of phase field model. The one that I will focus on is the one that collectively the community call AT1. So that AT stands for Ambrosio Tortorelli, who are responsible for the general form of this energy. And it's one because W of alpha is just a linear function of alpha here. Okay, so in case the link between the phase field and the free discontinuity problems are not clear, this little picture to the bottom right of the screen is really an example of a phase field computation. So what you're seeing is the alpha field, blue corresponding to 0, red corresponding to 1, for a problem which is just a uniaxial tension of a domain with a notch. So what you would expect is when you stretch this domain horizontally, at some point it's going to break at its shortest cross section. And so you see two example computation with two very different value of the parameter L. And when in both cases, even though it's not really clear from this bottom right picture, but the alpha field is a smooth function, but it's a smooth function that focuses, well, whose transition from 0 to 1 focus more and more along the line. So it's sometimes these are called diffuse interface method. That's a way to represent a sharp quantity, a curve by a smooth function. Okay, so all this is implemented in a code that I've developed for a long time. I won't go through all the details, but just want to mention that so this fracture code, MICDE VDEF, is open source, and you can download it here. You can even download a Docker image, so you can really be running a fracture problem in half an hour starting from nothing, if that's something you're interested in. Okay, so that's great, but does it work? Well, to a large extent, it works really well. So this is an example of, this is called a compact tension experiment. So you have a sample, a rectangular place with a notch, 3 holes, and right?
Blaise,
yes.
I think there's a question. Is that okay?
Yes, sure,
Robert?
of course.
May I ask, there's an underlying discretization of the domain, and what form is it?
Okay, so well, it doesn't really matter because I do solid mechanics. I use finite elements because I want to be able to handle complex geometries in 2 and 3D. So my code uses triangular or tetrahedral first or second order finite elements. I think all the examples that almost all the examples that I will show use linear finite elements. That works fine enough.
Thank you.
Blaise, you're not really adapting them to the crack as it evolves or anything. You don't have to, right?
At this point, I'm not doing any of this, and we could discuss that, but there's something really dangerous in doing mesh adaptation because you're doing a minimization problem. If you do mesh adaptation during your minimization, there's a chance that your changing the energy that you're minimizing at the same time you're minimizing. And that becomes the classical problem of the dog wagging the tail or the tail wagging the dog. It's not clear whether you're optimizing because you're refining or you're refining because you're optimizing. I don't know how to answer this question, so I'm doing the most naive thing, is throwing a lot of elements and be patient.
One more. The sequence we're watching, are these
Yes.
Iterations of a steady state problem, or are these time steps in a time-dependent simulation of the crack?
Both. So this is quasi-static. So you're assuming that at each time you achieve equilibrium, so we fix a time step, we minimize the energy, get to a critical point, increase the time step, do that again over and over and over. So you're seeing a large number of time step that I use to reconstruct this evolution.
And the left and right are the two different values of L, or?
So the left and right, so left, yeah, sorry, that's a bad professional disease from doing solid mechanics. Left is the Crite geometry in the reference configuration, and right is the Crite geometry in the deformed configuration. You see, well, you see there's this opening here increased a teeny weeny bit as time evolves. Okay.
If it's Blaise, if I may just jump in, it's Krishna Gadikipati. Yeah, with regard to your comment about mesh refinement, I'm sure as you're aware, there are approaches to mesh refinement which bring in notions of configuration changes and all of that, right? So one can do that also in a variational sense. I don't know if that has been coupled in with the underlying variational approach to phase field methods, but there is that branch of it.
Okay, the problem is that there are two terms in the discretization error. There's one term that is really the finite time in discretization. There's another term that comes from the phase field approximation. Yeah. And you'd better be really, really careful if you start messing with one with the other one. And I can easily construct example where any mesh adaptation scheme will give you a completely wrong crite path. It's really, really tricky, and that's because
even some of the methods that are variationally based that where the mesh adaptation. Yeah.
Yes, because when you adapt your mesh, you change the energy.
Sure, no, I understand that.
And it's easy to do that in a way that will lead you to the wrong solution. And in particular, because you don't have smoothness in time of the evolution and so on. So you're essentially putting yourself in some branch of solution, which may not be the right one. Okay. I just want to show quickly, and I'll only focus on the left picture, still going back to how does it work? Is it predictive? So to the left, so these are two computations that were done by a group of students at Caltech, Changzhen Sui and Neil Brodnik. And we were looking at, for some reason, crite propagation in a domain with inclusion. And that's a really classical fracture mechanics problem. It's well known that if you put a hole near the crite path, depending on how far from the axis of the path, your crite may be attracted or repelled or may actually intersect and so on. And so we generated a geometry. They used 3D printing to generate a sample, created an initial crite, did the first computation. So the color line is the crite that was predicted. I hope you can see this black line that corresponds to the fracture. And we thought that it was okay, but then what happened is when they really looked closely at the sample, they realized that because of the inaccuracy of 3D printing, the initial crite in their sample was not where it was meant to be, and it didn't match the one in the numerics. So they redid a series of computation where the initial crite is this red line here, where they actually placed the initial crite in the mesh domain based on the scan of the geometry. And so now here is the crite path compared to the experiment. Okay, so we're still a little bit off in this region, but I think this is still pretty darn good. Okay, that will qualify as a part of my success, or the success. Okay. The strength of this type of approach is because we're not trying to compute some kind of asymptotic expansion of the stress near a crack tip and so on. We can tackle problems that are much more complicated. And the type of problem that I'm really interested in are what I call diffusion-driven fracture. And that can encompass a really, really broad range of problems. But that's the idea of a fracture problem where the driving force, or the not driving force in the mechanics standpoint, but where the driving phenomenon is not necessarily a boundary load, but maybe something much more complicated. So for instance, think of mud cracks. So mud cracks are driven by evaporation in a slurry. When the water evaporates, the slurry contracts, it creates tensile stresses and crack grow. Something that I discovered moving up north is fracture in concrete due to freezing and defreezing due to the oxidation of the rebar. To the right is picture that my former student Ata Mesganejad sent me, and it's the fracture of in silicon nanowires in batteries. So these are little cylinder that's a swell for some mechanism that I don't understand in the battery, but in doing so, they observe a generation of cracks. So again, here, if you want an abstract version of that, would be to introduce a diffusive field P that, for instance, would solve a classical diffusion equation, but in a domain that depends on the crack, and then account for it. So here I suggested to account for it as an inelastic strain. So for instance, that would be a good example for the mud cracks. If you think of P as a water pressure, this is just your Darcy law and the mechanical energy here. Okay, so example of that would be thermal cracks. So this, I like this experiment because it's something you technically could do in your kitchen. It was, I think, initially proposed by McMaster in the mid-80s. Take a plate of glass, you heat it up, and then you put it in contact with dry ice. So you see the plate of glass, this is a dry ice bath. And the thermal shock creates tensile stress at the bottom, and you see this networks of crack that first nucleate and then grow. But as the cold front diffuses, there's less and less drive to grow crack. So you see this parking phenomenon where the number of crack that propagate is halved at regular interval. And there's tons of work on that, or you can do that on slightly thicker sample. So these are ceramic slabs that have been quenched. So this would be, let's say, the upper face, the face towards me, the lower face, the face towards you, and then against the upper face of a sample. So you unroll it, and you see this transverse, so long transverse crack, but also this crazing pattern on the side. So black is the material, white is the cracks. Again, in this case, actually I should have mentioned that. Yeah. So in this case, the cracks are expected to grow orthogonal to the temperature level line. So the heat flux on the crack is very small. So you can completely neglect it. Traditionally, that's the way it's been done. And if you neglect it, you see that essentially your diffusion problem does not involve gamma anymore. So it's a one-way coupling problem. You can solve the heat equation offline and then plug the P as a source term in your fracture energy. And so if you do that, so to the right is actually a sample of a scan of a sample. To the left is a numerical simulation. And the way you can quantify the difference between these, or the geometry of the crack pattern, is by drawing a line at a fixed distance of the free edge and counting the crack that intersect this line. So that gives you spacing, crack spacing as a function of the distance to the exposed edge. So this would be the distance from the free edge. This would be the crack spacing. It's normalized in some form. The purple square are the measurement by a group at the Chinese Academy of Science in Beijing. And the green dots are our numerical simulation. So again, complicated problem, lots of crack growing, nucleation of cracks, but we get a very, very good approximation. To get an idea, I think at this point, we're less than 1/10 of a millimeter away from the edge. So the fact that there's no measurement is probably just a sign that there's no way to take measurements so close to that. And then what we can do is we can look at closer region around this edge, for instance. Okay, so let's say I only try to simulate, I only try to simulate a piece of the edge, but do 3D computation. And what I want to see is if I would be able to reproduce this crazy pattern here. And the answer is yes. And what you see is that if you increase the magnitude of the field, you would go from simple network of transverse crack, still with this selection principle, you see that some cracks stop early and some cracks continue growing, to a situation where you have that, but you also have this complicated three-dimensional pattern. And then you can go even smaller. You can try to look at the even smaller scale, what happened next to the boundary. So that's a 3D computation. What you think of this as being inside the material and seeing the crack pattern growing towards you. And the color is just the elevation. It will help us doing some kind of post-mortem analysis. Okay, so we see tiny little cracks going towards you and some kind of coarsening and coarsening and coarsening. Okay, and so if I go to the end, so you see, for instance, here you have 3 cracks that have merged into 1 cell, then these 2 cell merged, then these 3 cell merged, then these 1, 2, 3, 4 cell merged, and so on. So you have the equivalent of this selection principle in 2D, but in 3D. So I cannot show a quantitative comparison with experiment because I still haven't found a way to do good quality 3D imaging of this sample and really identify the very complicated crack pattern. Okay. Okay. I'll quickly go through that. So we've applied that to many other problems. One problem that I really like is the problem of laser cutting of glass. That was a collaboration with a glassmaker in Japan. And the idea is, if you think of it as an example of where fracture is important, is not a bad thing, is that nobody knows how to cut glass. We know how to melt it and we know how to break it. And typically, the way you cut glass is you do controlled fracture. So you can score and break, but scoring and breaking is great for rectangles. But you know, this is not a rectangle of glass. So if you want to do something like that, you need a better method. And what the glass industry is trying to do is to use a laser beam. And the idea is to shine a laser beam along the crack of a path. The laser beam causes thermal expansion ahead of the crack or behind the crack tip. And this will, in terms, either pull or push the crack. They have demonstration of this, but it's really hard to control the path. It's not, there's a weak pinning between the laser beam and the crack, so it's not clear that the crack will exactly follow the beam, or sometimes it may deviate and so on. And okay, I'll just talk about this picture, but this is an example. What I'm showing here is just one little piece of a very large domain. And I've been trying to grow a crack through laser cutting close to the edge. So the lines are the contour line of the temperature field. And this curve is the crack. And what you see is that we can predict the deviation of the crack path numerically. Of course, the next step is the inverse problem, is where do we want to move the laser beam so that the crack, for instance, grows along this straight line. And this is clearly a complicated and open problem, but something, in my opinion, is very interesting. Okay. Quickly, if you want to do a little bit of mathematics on this problem and solve the fully coupled problem, everything that I've shown so far was a one-way coupling. That is, I was not really accounting for the crack geometry in a heat transfer problem. So let's go back to our diffusion-driven fracture problem. So we want to minimize some energy that depends on U, the displacement, P, the diffusive field, and gamma, the crack. subject to a state equation, which is a parabolic equation, in a domain that itself depends on gamma. The difficulty with that is, well, it's so you now have to couple this minimization problem with the parabolic evolution, and all the tools that we use for the study of the fracture problem come from the calculus of variation. So the very, very natural ways to reformulate your parabolic equation in terms of minimizing motion. So if you want to discretize forward in time, backward in time, no, forward, you discretize forward in time, and you interpret the discrete problem as the Euler-Lagrange equation for a minimization problem. And now you end up with a bilevel minimization problem. So inf of E of U, P, and gamma, subject to the fact that P is itself the infimum of a, a solution of a minimization problem. Okay, so we know how to regularize these by gamma convergence. That's the Ambrosio-Tortorelli function. It's not very complicated to figure out how to do the same thing for the F. Well, if you want to have this integral omega minus gamma, you can just multiply by a term that vanishes along gamma, and okay, you can show the gamma convergence of FL to F. That's trivial. Well, that's simple. Unfortunately, gamma convergence of a function and its constraint does not imply convergence of the constraint minimizer. Something we didn't really think first, and we're not the only one. Lots of people in this business are looking at this two-level optimization problem and just approximate each level separately and don't try to show convergence. So it turns out that for this example, essentially we can show some form of compatibility in the gamma convergence. And so without going into the technical detail, what happens is that we can show that we can use the same recovery sequence for both problems. And so that we're actually able to show convergence of minimizer, of solution of the constraint minimization problem. So now you have this couple problem, and the way we do it is we split the unknown because U, and think of U as the primal variable, think of alpha and P as two-state variable, and they're not as strongly coupled as U and alpha. And in particular, F is convex with respect to alpha and Q separately. So it's not too hard to minimize with respect to minimize EL with respect to alpha and P under this constraint directly using an adjoint based Newton solver. So you write the second adjoint problem and so on. It works. That was the thesis of one of my last students at LSU, Alex Dunkel. And I just want to show examples. So this is a simpler version. This is a scalar version problem. The level lines are the lines are the level line of the diffusion field, of the P field, and the color is just the fracture. And okay, the way this is designed, it's designed so that you have competition between two problems. The mechanics problem wants the crack to grow horizontally. The thermal problem, you want your crack to grow diagonally. And then there's this free discontinuity principle that says when a crack gets close to an interface, it wants to shoot toward the boundary of the interface. So that's where you get this complicated pattern, but I just want to insist on the fact that you really see that, sorry, this is a couple problem simply by looking at this. So you see that you have a complex crack path, but the level lines of the P field are orthogonal to the crack near the crack. So it really means that you actually do recover dPdn equals 0 along the fracture in the limit. Okay, I have 10 minutes. Okay, well, I'm just going to say a few words about open problem, and one of the challenges is nucleation. And the issue is that really propagation is governed by the toughness parameter, the GC. That's a given. But Griffith's theory is really incompatible with the idea of nucleation. In particular, it's incompatible with the idea of nucleation being governed by something called a strength. And if you go to the Home Depot and buy some wire or some cable, you will get a limit load that is given in pounds or metric equivalent. But essentially, it tells you what is the maximum stress that your material can sustain before it breaks. And I can quickly describe the incompatibility between these two concepts by looking at classical elliptic regularity issues. So what you'll see is something you can find in any good book on the topic. But if you look at the domain with a reentrant corner like that, and we're assuming that it's loaded in mode 1, so you stretch something that has a V reentrant corner like that, and you can show that if you do a blow up near the crack tip, the displacement in polar coordinates will be of the form sigma infinity. So that's the applied load plus some r to some power lambda, which depend on omega. And you can compute this lambda as a function of omega. That's this curve. So it goes from 1/2 when omega equals 0, that's a crack, to 1 when omega equals pi/2. That is, you just have a flat interface. If u is in r to the lambda, sigma is in r to the lambda minus 1, then the elastic energy density is integral of sigma square. So it's in, if you look at the restriction of if you look at the elastic energy density in a ball of radius rho centered around the crack tip, is going to be in rho to the 2 lambda. And then you play the trade-off game, introduce a crack of radius lambda, so that adds something, crack of radius rho that adds something of O of rho to the energy, but may release up to rho to the 2 lambda. And it's instantly, you see that you can only nucleate a crack if lambda is equal to 1/2. And worst of all, so lambda equals 1/2, that corresponds to a crack. So in Griffith's theory, if you don't have an initial crack, you will never get a crack. But at the same time, if you have simply a notch like that, your stress will be infinite. So if you were believing the concept of strength, you would need to be able to, so you would have to nucleate a crack for any non-zero loading. And okay, we're mathematicians, so it makes sense. I mean, having a criterion that is based on a pointwise gradient of a function in W12 makes absolutely no sense. Okay, I'm trying to get to what I want to do. Okay, it turns out that you can actually do some analysis of the nucleation problem. And so what you can do is to look at the 1D problem. And for 1D problem, you can solve the 1D evolution in closed form. And you can show that there are 4 types of solutions. So I take a beam in the Ambrosio toroid, I stretch it. And the 4 types of solutions are elastic. So elastic means alpha is equal to 0. And it only exists under a threshold. Then you have what I call homogeneous damage. That is the damage, the alpha parameter, the older parameter is constant. The displacement is still linear. Then what I would call partially localized, that is your alpha, your order parameter, is a smooth function, but whose maximum is not 1. And then what I call a fully localized, so that would be a function that goes all the way to 1 and back to 0. So that's what we think of a phase field crack. You see this analysis done in pretty much any paper that's been published since 2010 on the field. What's missing to most paper, and it's done very beautifully in this string of paper by Corrado Morini, Kim Pham, Jean-Jacques Marigot, and so on, is the stability analysis. And again, I wanted to get to this one because it's pretty important. Because we have a variational theory and not something based on criticality, we have another criterion to decide on which of these branch we want, and we want one that is stable. And so you can do a second order stability and show that the only stable type of solution are elastic of completely fractured. So on 1D, what you have is either a linear response or a crack. And the load at which your crack nucleates is given by, or the stress is given by this relation. So that if you, so GC is the toughness, E is the elastic modulus, L is the Young's modulus, L is the regularization parameter. If you know sigma C, GC, and E, you can compute an L such that the crack, numerically, the stress at which you will nucleate a crack match is equal to sigma C. So it's given by that.
So Blaise, sorry, Blaise, but we have just a couple of minutes left.
Yeah, that's why I'm trying to wrap it up. And I'll just show one picture, or maybe two. Okay, so this is exactly, let me see. Yeah, I'll just wrap it up with this. So this is a three-point bending problem for a domain that has a notch. For various values of the notch angle and the notch depth. None of these cases can be accounted for in the Griffith theory. The black dots are numeric, are physical experiments, so for various value of the notch angle and notch depth. The color dots are numerical simulation done. And again, we have 0 parameter we can fudge with. The 3 parameters that we have are Young's modulus, fracture toughness, and the L parameter. And the L parameter, we obtained it from the tensile stress. There's nothing free left. So we just plug that, we run our computation, and you see that we actually match the nucleation standpoint, the nucleation load for every single possible configuration. We can do the same thing. So I'll finish with this. So this is the same story, but with a U notch. So which is even more challenging because there's no stress singularity of anything. But there's this nice picture that shows essentially some scaling law for 18 type of materials, the nucleation over a U notch. And you see there's some kind of universal law that seems to happen. The black dots are the outcome of many of these experiments. The color dots are a result of phase field computation. And once again, no free parameter, but we still match the nucleation correctly. Okay, so, well, I'll stop here and essentially I focus too much on the success and not much on the challenge. The challenge is really to explain, to understand why this is working so well. I'm still in the
Thank you very much, Dr. Blaise. Yeah.
Thank you for your attention.
Thank you. So are there any questions? We have a couple of minutes. If you have questions, please unmute yourself and feel free to go ahead and ask. Maybe I can ask one until unless somebody else wants to. So Blaise, so you mentioned, of course, that one of the starting points was this ideas from image processing that were proved to be very useful. Now, in that literature, it's also, there's a lot of emphasis on also trying to find global minimizers for variation problems like this. And people have come up with ideas for relaxations, convex relaxations, and so on. Do those approaches have any role to play in these crack propagation problems as well?
So that is actually one of the really big open problems, is that, I mean, it's not really a surprise, but you can show that global minimization will lead to major paradox. So from a modeling standpoint, it's clear that global minimization is not the right thing to do. From a mathematical standpoint, if you get rid of global minimization, essentially you lose calculus of variation. So we're completely in the Wild West. And this is another of the really challenges in the field right now. The mathematical theory is based on global minimization. We can easily show that this is not what it's supposed to be. but we don't know how to formulate a well-posed theory based on anything other than global minimization. Intuitively, we would want to be some kind of meta-stability of equilibrium state or following branches of equilibrium state. I don't know how to formulate that rigorously mathematically, and I don't think anybody knows how to do that at the moment.
Thank you. Are there other questions?
Hi, this is Xiaoxuan speaking. Thanks for this nice talk. Can I ask you a question? Could you comment on how to use extend a phase field fracture to the ductile fracture? What's your thought on that?
This is a very active field, and so there's been lots of work, including some of mine, on introducing plasticity, at least. So it's not too hard to add a plastic dissipation to the model, and we actually recover some interesting behavior this way. But ductile fracture typically is you go from an ad hoc continuum mechanics law. So doing the equivalent for ductile fracture to what has been done by Griffith is an open problem, but I'm not sure this is the right thing to do. I do believe that the right thing to do is to revisit the foundation of ductile fracture, formulate a model, and show that in the limit it matches classical Paris and so on law, which to some extent has been done at least in a numerical / ad hoc way. The analysis is crazy difficult.
Thanks for the comment.
You're welcome.
Are there any quick questions?
Just
Krishna?
one very quick one. Thanks, Selim. Blaise, of course, really nice talk, and you're right. You're the right person to be doing this. What about nonlinear elasticity when it comes to what I'm talking the reasons for all the issues with existence and regularity of solutions for nonlinear elasticity itself? Now, when you couple it in with phase
so
field.
Actually, surprisingly, existence of solution in nonlinear elasticity was obtained really early on. What was really difficult is to go to linearized elasticity. And that kind of makes sense because you end up with locally large deformation. But now so that's the mathematical analysis. From the mechanics standpoint, does it make sense to go to nonlinear elasticity and still keep an ad hoc surface term? I'm not sure. Well, I have some idea. I'm not convinced because Griffith essentially you're bundling lots of really complicated stuff. You're putting everything under the rug and you call it GC. So you're neglecting tons of physics. Yeah. So is it more important to properly account for, let's say, large deformation and still doing this dirty trick, or do you need to first get a better modeling for what happens near the fracture before you talk about a nonlinear effect on the elastic field? I'm not sure. I'm not a real mechanician, so I can't really answer this question.
Okay.
There's one more question in the chat from Vera. Sorry, I mispronounced Sundararahapan. He's walking outside, so he cannot unmute himself. But he.
Oh, Vera, that's a really good question. Is it a material value or numerical only? Both. It really is both, and this dual nature, and that's what makes it really fascinating. Is that you can think of the length scale as a numerical parameter because it's it's a regularization length that you need to send to 0 to obtain conversion to Griffith. But there's a link between this other parameter, or between the length scale and nucleation. And at the same time, there is a really interesting series of papers by Marigot and his former student, Paul Sixi, essentially showed that if all goes well and if you use the proper phase field type of formulation, you can recover Griffith, G equals GC, even for a fixed value of the length scale parameter. So then it sends the message that, yeah, you can probably think of the length scale as some material value, material parameter, and use it for something else.
Hey everyone, we went over a few minutes, so perhaps this is the time to thank Blaise one more time for a very nice talk. Thank you, Blaise.
Thanks for your hospitality.
Thank you very much.